Hello and welcome back to hardware design. We are going to continue working. We're going to continue working on our uniform probability arbiter. Let's see. So last time, what we were working on was building a priority encoder, something that could convert strings of ones and zeros into one-hot signals, and what that code looked like. So we have this static priority unit, sort of like this. So let's see if we can't so make gen module name equals static priority. So making the static priority module, and then we'll show you what the resulting Verilog looks like. So this is what the commented out static priority looks like, where it's just table-based lookups. So A15, it should return a string where the leading bit is 1, 14 is 1, and we're playing some math tricks here to make that work. And then the logic-based version is pretty similar. It sort of says, well, you know, is Z15 is 15 if A15 is 1, otherwise it's A14 as long as these strings are not 1. So that's what the code we wrote last time looks like. So what we would like to do is work on our round robin unit. So the way that we're going to start that is we're going to just copy over. We're going to copy the way that we were verifying static priority, and we'll call this uniform arbiter. And then we will RTL, and then we will copy static priority.vp to uniform arbiter.vp. Good. So we're just going to do a little bit of cleanup here in the verification test bench for static priority. So what the first goal is to just get a excuse me, a very simple test bench working, so that we can really quickly check whether or not something bad is happening with our design. And then later on, what we'll do is we'll go and build something more comprehensive. And the only rules I think we have for our design, is that the value be defined in not one hot. So we can uncomment these assertions. It's probably wise to guard these in case we're in reset. So reset is active low. That's not how that key works. There we go. So that should help us out. And then the only thing we were missing was a reset. So initial begin and reset equals 1 bit 1, reset equals 1 bit 0. Then we could do repeat 10 at pause edge clock, so I'll wait 10 clock edges, and reset will go back high. So really quick and dirty reset. So I think that's all we need in here. So we have A and Z. We have a random vector to hit on A. We could be more clever, and then we have some stuff printing out. Good. So now we have our uniform arbiter. So one of the ways that we're going to make our arbiter more uniform is that we are going to have some state to help us out. So if we're going to have some state, we need clock, and if we're going to reset that state, we need reset. So that's that. So we need to do a few things here. So the first thing we need to do is build a. So before we talked about a barrel shift based on history. Then we're going to do a priority encoder from before. 3 is barrel shift the result back. And then 4 is store the last winner. It's not too bad. So we'll fill in the easy ones first. Fix some spelling mistakes. There we go. Yeah, close enough. So we want to instantiate our module from before. So my static priority is generate static priority. And then the parameter that determines the bit width is just bit width. So we would write bit width less than equals $BW. So now we've set the bit width to bit width, and then we can instantiate. So my $SP instantiate. And then we need to decide what we are going to put on these. All right. So we're probably going to need some intermediates. So so one of them is going to be the shifted version of A. So we'll call that A under shift. And similarly, we'll have the shifted outputs. So that is what we will put into the unit here. All right. And then we want to store the last winner. So this is another easy one to do. My dollar DW generate DFF, and then I always forget it is width with a capital W. Instantiate the flip-flop, and then we need to set up the ports, so we should double check to see what those ports even were. So this one is DN clock reset Q. DN dot clock dot reset z.q. So we know that the input needs to be z. This is just clock. This is just reset. We'll call this z under last because it is the z from last cycle. Great. So now we just need to do these two conditional shifts. So let's do this the easiest way I could imagine. So we're going to play our trick again. Always come again end. I'm going to build a unique case statement. 1-bit-1. We're going to close that before we run into any issues. We'll add a default case here where we'll say that a shift is equal to a. And then we need to define all the other cases. So what we'll do is we'll iterate over all the other cases. $I less than $BW, $I plus plus. And so the case is if z under last tick $I, so that is the last winner. So what we put here is the resulting expression. Now I think I actually want to skip case 0 because that would be an awkward one to write. Because if z0 1, that means the lowest priority one. And so the scheme that we're doing is that we're going to shift the priority so that the last winner is the lowest priority. Right, so let's write a little note, shift such that the shifted priority makes the last winner the lowest priority. So if it's z0, then we're just going to say that a under shift equals a. So since that's captured in the default case, we can just ignore that. So this is z equals last z 0 or all zeros. Cool. So then what this would be is this would be $I minus 1 colon 0 concatenated with u minus 1 to $I. So what this is saying is concatenate the string, concatenate these two chunks. So this chunk where we're starting to the bit just to the right of I, take that all the way to 0, and then add to the back the leading bit, BW minus 1, all the way to I, so that no matter how we shift it, I will be in the lowest position. All right. So far, so good. Then we got to do that again here, but we need to go the opposite way. So this is probably the one that I'm going to muck up. then we messed up the syntax up here. So the string matches on Z last, and then we're making a shift equal to that. Good, 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 good. All right, so this was the easy one. And then now we need to do the hard one. So those are the right names. All right, so here's some, let's see. So I think, yeah, so this certainly needs to be BW, so that's coming back. Ooh, so I have a fun puzzle here that I did not prepare in advance, so I don't know off the top of my head, so you'll run into this sometimes. So when you do run into these, what it's easiest to do is just to run through some simple examples. So let's imagine the case where Z last 10, right? So that means that A under shift is really going to be A from 9 to 0, and then A from, we'll say 31 to 10. Okay, great. And then what we'd like Z to be then is we need to put everything back. So I need to take the bottom bits and then put them back at the top. So that would be Z under shift. So one of them is 0, so that's the easy one. And then this one is 31 minus 10, so that would be 21. And then we would concatenate that with 31 to 22. Okay, so I think that's probably all we need. So I think let's delete the ones that we aren't sure of and then keep the ones that we are. So this stays 0. This stays BW minus 1. So these two fields are the ones that changed. So 21 is roughly BW minus 1 minus I. So we're just going to write that, BW minus 1 minus $I. Perfect. And then 22 is BW minus I. All right, so let's hope that that's pretty reasonable. So we'll generate that RTL first. So we're going to call this is called uniform arbiter. Boo. All right. So it looks like I did not close backticks. There we go. And I made the same mistake up there. So that's the problem with copy paste, is that you end up copy and pasting all of your sins. All right. So we're running the generator, running the generator. So I'm looking through these warnings. Parameter 16 was passed to top uniform arbiter dot my uniform arbiter dot width, but it was never actually declared or used in width. So what is going on here? It was a parsing error. So this is DW. So this has to be module name, instance name, parameter. So did we muck this up? Yeah. Sometimes it'll be width must be an array. Good call. So I think that's about it. So let's take a look at the generated uniform arbiter. Does it conform to what we expect? So Z1 should put 0 first. Yeah, so this looks about right. So this should walk, and this should walk as well. Hopefully it doesn't get too upset about this. I don't want to have to write too many special cases. I kind of like the compact version that I have. All right, this is does this make sense? Well, we'll see. All right, so let's double check our top uniform arbiter to make sure that it's doing something sane. Yep, so this is just saying that the winner must be from the input and one hot. Okay. Make run. So, grep offending, star.log. So it looks like we passed. So it looks like we wrote that the first couple times. You can kind of see the behavior that we've implemented where it sort of moves the priority left to right. So you kind of get this rippling along where first it favors high, and then it starts going lower and lower, and then it circles back around. So it certainly looks like the priority is varying. Let's I'm just going to take a tighter look at the log. So the third bit. So if the third bit was 1 and then that 1, then the new highest priority should be the next bit over. Oh, interesting. But this might be during reset. Yeah, so these first 10 are during reset. So there should be a set of these. Yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are during the reset period. So the flop that is holding the last winner is held constantly at 0. So that's why the priority isn't changing. But as soon as it gets here, so this is the first one that wasn't in reset, it ripples. And so, yep. And so it appears to be rippling into the right position. So that would say like these 2 bits better be 0, and that string, yep. So this, the first order, this looks really correct. So you know, that to some degree, the you know, our arbiter is doing exactly what we promised, and it's certainly different than our you know, our static priority. Boo. Where its output was, aside from having all those assertion errors, where it favored this left side. So it's certainly doing a more fair job. So then the next question is, well, how do you know? Right. So if you're logging in, you've probably logged in for the intimation that this was a uniform probability arbiter. And if you've been reading up on Wikipedia about arbiters, you probably saw that this is sort of like the round robin arbiter. The big difference being that I think the classical round robin arbiter always shifts by 1, and we shift by a variable amount to kind of get around some weird issues that happen every now and then. But that's more or less my intuition for why to do it that way. And it's the one I wanted to build. So how do we know that it's uniform, right? So the only tests that we have running are that, you know, if we're not in reset, the output better be defined, and that the output better be a singleton winner that was bid, right? So this is just saying we had a legal output. So what we kind of need to do is verify whether or not this actually had uniform probability. Oh, cool, that's there. I didn't realize the waveform viewer was there. Cool. So how are we going to do that? So we're going to need to do two things to our test bench, because right now our test bench is just putting random numbers on the input, right? So one thing is, you know, this probably needs to be more clever. You know, probably needs to be clever. Period. And so, you know, should think of like a worst case scenario. Yeah, so try and think of scenario where, you know, it's unlikely that we're going to do well. The scenario that I generally like is a sliding window. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So it looks sort of like this. And you just kind of rotate through this pattern. And there are two ways to do it. So one is use this pattern directly, or we could mask random with, not mask, you know, we could, you know, take, you know, the bit pattern here and just end it with random, you know, and that could potentially be, you know, kind of interesting, because then there's a, you know, you're not guaranteed to be a walking 1 pattern. The other interesting thing to do is to kind of randomly restart this pattern, because certainly something like a you know, a round robin where it has incremental priority is actually going to do fairly well as long as it accidentally lines up on the leading bit. You know, it's almost going to look uniform in the global scale. It's going to look like we're sort of walking along and satisfying things as they come along. And so we could really mess that pattern up by constantly restarting it, so it has no idea where the right spot to be is in the middle. So that's one of the things we need to do to get us where we're going. The other thing that we need to do is we need to add some tests. So we need to test the statistics of the arbiter. And specifically what we're interested in is that the expectation of a win, or probably better said, the sum of the expectation of wins is pretty close to the number of wins, per bit. So the idea is we need to keep count of how many people, how many bids win, and then every time a bid is made, we need to increment the expectation that there would be a winner. And then we would sort of compare the two, is that we'd expect the expected, our thought is that if there really is a uniform probability that this is being evenly treated, that it lines up and that we don't need to worry too much about this sort of going on. And I think something that we haven't really stated is we probably also need to make this much longer if we are interested in doing any sort of statistical analysis. Right, so if we have 1,000, we could actually be off by a fair amount just accidentally dealing with random. If it were deterministic, we could probably have a better sense of what should happen, but 1,000 seems kind of small. The actual opportunities for an individual bit to win are fairly tiny, right? So if we do a 20-bit vector, then there's only 50 opportunities for each bit to win if it's evenly distributed. And then if we're doing something sort of random, that could be off by 10 or 15 in each direction, and so our power would, the power of that analysis would be pretty small, because we'd only be able to say, well, it's fair within 20%, so it has a 20% fairness. If we were to kind of do this at a production scale, what we would need to do to make this production worthy is we would need to think about all of the tests that we would want to run. So I think it's been a while, but I think Bill Daly has a textbook on network design, and I think I would need to look it up, but I think that there are some worst case traffic patterns from that. And then if you're a company like Cisco or Qualcomm or Intel and NVIDIA with respect to their own interconnects, they would have worst case traffic patterns against these arbiters. So the reason that networks come up when you talk about arbiters is you can think about a router as being a structural hazard, that for every link coming into the router, there's only so many resources to route it to an output. So everybody needs to arbitrate on who gets to go. And then if the arbiter favors one side too much, it might create blockages or performance pitfalls. So I think that's sort of a nice and sweet. That's a short little implementation we did today. So we went through the uniform arbiter. We sort of built this one hot encoded barrel shift and this other one hot encoded unbarrel shift. We hooked it together and built what we think is going to be a uniform probability arbiter. And what we'll do next time, on hardware design, is let's test our fairness, and hopefully we can be like 1% fair. That most of the time the statistics sort of line up. And so part of the testing that fairness is adding new test vectors and calculating some statistics. And certainly I think if I'm well slept and well caffeinated, that should be the last video on the fair arbiter, unless we fail to hit 1%, and then we can sort of talk about how we're going to fix that. So we'll, if it turns out we're not fair, I'll have to do some reading to find out the right way to, not the right way, but a different arbiter to build that is more fair than our arbitrary objective of 1%. And certainly feel free to suggest either in the comments on the video, or I think I have a Reddit post somewhere if you're getting here from Reddit, or tweet at me. If there's something else that you'd like to see me design after the fair arbiter, that's good. If not, I might go back to building the rasterizer, or if one of my research students has something fun that they like to see me build. They aren't watching, but they like when the widgets are done that they can use for their stuff. We'll do one of those. But otherwise, have a wonderful Wednesday evening, and I will see you all next time.